This video will accompany the Chapter 6 notes over probability distributions. In this module, we're going to begin to develop a set of tools that will allow us to take the information contained in the sample to say something reasonable about what is occurring in the population. We will accomplish this by studying the behavior of the statistic and then see what the behavior of the statistic suggests about the parameter. Notice that the parameter is the information we really want, but usually we only get to observe the statistic. In section 6.1, we're going to look at summarizing possible outcomes and their probabilities. Recall that the reason we are discussing some of the basics of probability is that before collecting the sample, we do not know what the value of the statistic will be, but we may be able to predict what will happen. We say the statistic is random since we do not know the value before collecting the sample. More specifically, we can think of the statistic as a random variable. For example, suppose we're going to go out and collect butterflies. Prior to looking at the butterflies, we don't know which butterflies will be in our sample. Further, suppose that we're interested in the weight of the butterflies that we collect. Well, before going out and actually collecting the butterflies, there's no way to know what that weight will be. A random variable is a numeric measurement of the outcome of a random phenomenon. Often, randomness results from the use of random sampling or a randomized experiment to gather data. So here we can think of the weight of butterflies as being a random variable, since before collecting the butterflies, we don't know what the value of the weight will be. A discrete random variable is a random variable whose possible values can be listed, i.e. a random variable that can assume only a finite number of values or a countable number of values. Here we use the definition of discrete random variable, very similar to the definition of discrete variable. The only difference here is we say that it is random because before actually collecting the sample, we don't know the exact value. On the other hand, a continuous random variable is a random variable whose possible values form some interval of numbers. So here, the weight of the butterflies is a continuous random variable. The sample space of a random variable x tells us what values x can take and how to assign probabilities to those values. One thing to note, because there is a limit to the accuracy of any measurement instrument, such as a scale or a watch, it may seem that any variable should be thought of as discrete. However, when there are a large number of closely spaced values, the variables of behavior is assumed to be continuous. We will use capital letters for the names of random variables and lowercase letters to represent the actual values the variable may take. For example, if we are interested in seeing the probability that the random variable x takes the value 2, we use the notation from earlier to write p, open parentheses, which represents the probability. Inside the parentheses, we have x is equal to 2. Read as a sentence, this says the probability that the random variable x equals 2. Take a moment and see if you can answer the next couple questions on your own. For each of the following, decide whether the random variable is discrete or continuous. When you come back, we'll look at the answers together. The first one we have is the random variable x equals the sum of the faces on 2 die. Well, previously in Chapter 5, we saw the possible values that x can take are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Notice this is a list of numbers. They do not constitute an interval, so this is a discrete random variable. B, the random variable y equals 0 if a coin lands on heads, and 1 if it lands on tails. Again, our only possible outcomes here are 0 and 1. These do not create an interval. This is a discrete random variable. The random variable, capital N, equals the number of sandwiches sold at a local restaurant today. Notice that the restaurant could sell no sandwiches. Some restaurants allow people to order a half sandwich, so they could sell a half of a sandwich, 1 sandwich, 1.5, 2, 2.5, and so on. Notice that this does constitute a list of values that are not on an interval. These are not on an interval because, for example, the store could not sell 1.6842 sandwiches. So again, C is a discrete random variable. The random variable X equals the amount of water in gallons you use to shower next week. This would be a continuous random variable. And then finally, E, the random variable Y equals the length of time in minutes. It takes a runner to run a 5K. This one is also a continuous random variable. Since a random variable refers to the outcomes of a random phenomenon, each possible outcome has a specific probability of occurring. The probability distribution of a random variable specifies its possible values and their probability. When a random variable has separate possible values, such as 0, 1, 2, 3, for the number of tails and 3 flips of a coin, it is called discrete. So notice we haven't changed our definition we had on the previous page. The probability distribution of a discrete random variable assigns a probability to each possible value. Each probability will always fall between 0 and 1 and are inclusive, meaning that some outcomes will have probability 0 and some could have probability 1. The sum of all the probabilities must equal 1. We let P of X denote the probability of a possible value X. So notice here you've got a box. This is the definition taken straight from your book. So let's look at an example. In some sports, playoff championships are decided by the best of 7 series, in which the team that is the first to get 4 victories wins the series. Let capital X represent the number of games needed to determine a winner in a best of 7 series. The probability distribution is given here. So notice here we're going to play 7 games, and the team to win the team to win 4 games first will be the winner. So it's possible that we play 4 games and one team wins the first 4 games, meaning they're the winner. It could also be that we have to play 5 games total, meaning that of the first 4 games, 3 were won by one team and 1 by the second, and then on the 5th game, the other team wins their 4th, making them the winner of the series. Here, we've got a distribution that tells us the probability of each of these potential outcomes. So here, these are given to you, these probabilities, these were not calculated. These are already given to you. So what this tells us is that the probability that the series of 7 games is won in just 4 games is equal to 1 out of 8. So the first thing we're going to do is we're going to show that this does in fact meet the definition of a probability distribution. And again, these probabilities were not calculated, this distribution is given to you. So let's confirm that this meets our definition. So notice that our definition has 3 different properties that we need to satisfy. First, a probability is assigned to each possible value. Here are the number of games that can be played in a series of 7. These are all of the possible values, and notice each possible value has a probability assigned to it. Next, all of the probabilities are between 0 and 1. Looking above, all of these probabilities are between 0 and 1. And then finally, the last thing we need is that the sum of the probabilities is equal to 1. So looking here, if we add up each of these values, we do find that that is equal to 1. So we have met the definition of a probability distribution. We can use the probability distribution to help us answer some questions. So for example, what is the probability that the best of 7 series will be decided by at least 6 games? Well, to be decided by at least 6 games, that means the minimum number of games played is 6. So they could play 6 or they could play 7. Just to find that probability, what we'll need to do is add together the probabilities for 6 games and 7 games. And you'll see that's what we've done here. So we find that the probability that a best of 7 series will be decided by at least 6 games is equal to 0.625. Just as we used mean to describe data sets, we can also talk about the mean of a probability distribution. To describe the characteristics of a probability distribution, we could use any of the numeric summaries defined in Chapter 2, mean, median, quartiles, and standard deviation. The most commonly used measure for center and variability are the mean and standard deviation, respectively. Recall that number summaries of populations are called parameters. You may think of a population distribution as a type of probability distribution, one that applies for selecting a subject at random from the population. Just like summaries from populations, numeric summaries of probability distributions are referred to as parameters. Note, we usually use Greek symbols to represent parameters. Recall that we use mu to represent the mean and sigma to represent the standard deviation. To calculate the mean of a probability distribution, we multiply each possible value of the random variable by its probability and then add up the product. Notice in your notes is a box from your book that describes this process. This is also known as a weighted average. The mean mu of a probability distribution is also called the expected value of x. So let's look at an example. Let x represent the number of homes a real estate agent sells during a given month. Based on previous sale records, the agent estimates the following. The probability of selling 0 houses is 0.68. The probability of selling a single house is 0.19, and so forth. Selling any higher number than 4 results in such negligible probabilities that they're considered 0 in this scenario. So first, we're going to confirm that this meets the definition of a probability distribution and explain why. So notice we've satisfied our 3 criteria we need to have a probability distribution. First, a probability is assigned to each possible value. So we see the possible values for the number of houses sold in a month are anywhere from 0 to 4, and each of those have a probability assigned to them. All of the probabilities are between 0 and 1. Again, notice that each of these values are between 0 and 1. And then finally, the sum of the probabilities must equal 1. So take a moment and confirm if we add these numbers together, we do in fact get 1. So this is a valid probability distribution. So now what we're going to do is we're going to look at how to calculate the mean of this probability distribution. So the agent supervisor calculates the mean as follows. They take the possible values of houses sold and divide by 5 and claim that on average the agent should be selling 2 homes per month. And so the question here, is the supervisor correct? Why or why not? Well, we're going to apply our definition of the mean of a probability distribution and see if this is correct. So we need to find what's known as the expected value. So recall, here is our probability distribution. To find the mean of this distribution, what we're going to do is take each potential value for the number of houses sold, for example 0, and multiply it by its corresponding probabilities. So we would take 0 times 0.68, and notice we have our first value here. Next, we'll take 1 times 0.19. That gives us our value here. Continuing, notice that we're taking each value and multiplying it by its probability. Doing so gives us 0.5. So notice here that the supervisor is wrong. The expected number of houses to be sold in a month is 0.5, not 2. So why is the supervisor's thinking incorrect? Well, notice here, if we look at our probability distribution, the supervisor is assuming that selling the number of houses, the probability of each potential value is equal. This is not the case. We see there's a 68% chance of selling no houses and only a 1% chance of selling 4. So when we talk about the mean of this probability distribution, we have to take into account the different probabilities for the different values. This is why the mean is also known as that weighted average. We're placing weights for each of the potential values. We can also talk about summarizing the variability of a probability distribution. As was true with sample data, it's useful to summarize the variability. The standard deviation of a probability distribution, sigma, measures the variability from the mean. Larger variability corresponds to larger standard deviations. Note, until later, we're not going to use the formulas for calculating standard deviation of the probability distribution. For now, you just need to know the property that larger standard deviations mean more variability. Smaller standard deviations mean less. We could also look at probability distributions of categorical variables. It's obvious when we have numeric values that we can use various calculations involving them. However, for categorical variables only having two outcomes, a success and a failure, it's often useful to represent these with 1 for success and 0 for failure. We can then do numeric calculations, and the formula for mean remains the same, and the value represents the probability of the outcome coded as 1. We will do more with this in later chapters. But for example, if we were thinking of flipping a coin as heads and tails, we could think of every time we see a heads writing down a 1, and every time we flip a tails writing down a 0. We are now going to shift our focus and talk about a continuous probability model. Continuous probability models assign probability as the area under a density curve. For continuous probability models, we will be interested in the probability a random variable occurs within a range of values. The probability of a random variable occurring within a range of values is the area under the curve, above the range of values. In previous modules, we saw how quantitative data can be visualized with a histogram or a dot plot. We can think of a density curve as a line that displays the general shape of the plot. We can use density curves to help us describe the pattern of continuous random variables. Density curves will have the following properties. The total area under the curve is equal to 1. The proportion of the data in any interval is the area over that interval, and the curve is always on or above the horizontal axis. There's an additional video listed in your notes with the QR code. If you're not familiar with the QR codes, these can be scanned using your cell phone if you've printed out the notes, or if you're on the computer, you can just click the link to the Khan Academy video. This Khan Academy video will give a helpful review of histograms, as well as an introduction to density curves. So let's look at an example. Suppose you want to randomly select a number between 0 and 8, where any number in the interval is possible. Notice that the sample space here is any number between and including 0 and 8. So for example, we could select the number 1.7824876551. First, notice that there is an infinite number of numbers between 0 and 8, and therefore the probability of selecting any single number is 0. Instead, we'll ask questions like, what is the probability that the number selected is between 2 and 3? We will assign probabilities to intervals. We will do this by equating the probability to the area under this density curve. In this case, the density curve can be represented by a rectangle, seen in the video. On the x-axis, we will have the sample space, i.e. the numbers 0 to 8. Recall that the area of any rectangle is given by the length times the width, where here the length is 8 along the bottom, and the width will be the height of the rectangle. Since the rectangle is a density curve, the total area under the curve is 1. So if the total area under the curve is 1, and we know here that our length is 8, using the properties of a rectangle, we know that the width here must be equal to 1/8. Notice this occurs because if we take our width times our length, we should get the area of the rectangle. So 1/8 times 8 is equal to 1, which is the correct area for this curve. We can find the probability that a randomly selected number occurs between 1.5 and 3.5. To find the probability, we first shade the corresponding region. So notice this is the region of the curve above the interval 1.5 to 3.5. This area represents the probability that we were interested in. So if we find the area of the blue rectangle, That will give us the probability that a randomly selected number occurs between 1.5 and 3.5. So to do this, we're going to take the width of the blue rectangle, which is equal to 1/8, times the length of the blue rectangle, which in this case is equal to 2. So notice here, we take that length times the width, and that tells us the probability that our random variable occurs between 1.5 and 3.5 is equal to 1/4. So let's do some examples. Suppose that the number of seconds it takes a person to unlock their phone X is uniformly distributed on the interval from 0 to 6. Here is a picture of the density curve. Pause the video and see if you can answer questions A through E. When you come back, we'll look at the answers together. So the first question is, what is the width of the density curve? Well, again, we know since this is a density curve, the area inside of this curve must be equal to 1. So if our length here is 6, that tells me my width must be equal to 1/6 in order to give me an area equal to 1. What is the probability that unlocking the phone takes more than 5 seconds? So what we're going to do is we're going to shade the rectangle that corresponds to this interval. Being greater than 5 seconds, that's the same as talking about the interval from 5 to 6, and we're going to shade the curve above that. Shading this area, notice here that we've got a length of 1 and we've got the height of 1/6. So taking the length times the height gives us the probability, which is 0.167 in this case. Next, we're going to look at the probability that unlocking the phone takes less than 2 seconds. Again, we're going to shade the portion of the curve along the x-axis that represents less than 2 seconds. And then we're going to draw the rectangle shading the area above that. Notice that the length of this rectangle is 2, and again, the width is 1/6. 2 times the 1/6 gives us our probability, which is 0.334. What is the probability that unlocking the phone takes between 3.2 and 5.7 seconds? Again, we've marked 3.2 and 5.7 along the x-axis. Again, sorry about that. And then notice here our width of our rectangle is still 1/6. So our length here is 2.5. Our width here is 1/6. Multiplying the values together gives us the area of the rectangle and tells us our probability is 0.42. What is the probability that unlocking the phone takes exactly 6.5 seconds? Well, notice that 6.5 is outside of our density curve, so we automatically know its probability is 6. But what if we had asked the question, what is the probability unlocking the phone takes exactly 4 seconds, which is inside of our interval? Remember that when working with continuous distributions, we're looking at probabilities over an interval. So the probability that x equals any exact value when working with a continuous distribution is going to be 0. Now you'll notice at the bottom of the page, it says you can watch a video of the solutions and gives you a link. You can watch that video. That video will go over what we just did, except in just a little bit more detail. That video is from a previous class, so the page number that I mentioned will not match up, but the problems are still the same. In section 6.2, we're going to look at probabilities for bell-shaped distributions. We're going to start by looking at a normal distribution, which is the most important of the bell-shaped distributions. A normal distribution has a symmetric bell-shaped density curve. Each normal distribution or normal curve has its own mean, which controls the center. The mean is usually denoted by the Greek letter mu, and standard deviation, which controls the spread. The standard deviation is usually denoted with the Greek letter sigma. So looking at a picture. The green curve, notice that it is centered at -2. And the standard deviation equals 0.7 to 1. Compared to the blue curve, it is wider because the green curve has a larger standard deviation. Notice that I'm getting these values from up here. The blue curve, again, notice it has a mu of equal to 0, is centered at 0, and has standard deviation equal to 0.45, which is the square root of 0.2, since they're giving variance in this picture. Compared to the green curve, it's going to be more narrow because the standard deviation is smaller. So again, to iterate, when we're talking about the standard deviation of our density curves, we're not so much worried about how to calculate them, but more what that standard deviation is telling us for now. Small standard deviations will result in curves that are less variable. Again, notice how the blue curve is kind of more pushed in. Larger standard deviations will result in the curve being more spread out. One thing to remember, the reason the blue curve is is taller in this case, is because since all of these are density curves, their total area has to be equal to 1. So if the area is the same, whenever we push the curve inward, it has to go up a little bit to preserve that area. We can use normal distributions to help describe the patterns that different variables follow. If a variable follows a normal distribution, we can use the following shorthand notation. This notation reads just like a sentence, so let's look at the different pieces. First of all, the variable, this is what you're describing. It could be data or it could be statistics. The tilde here reads as follows a pattern. The capital N means normal. The mean tells us where that normal distribution is centered, and the standard deviation tells us how far spread out the curve is. So reading this as a sentence, this would say that the variable follows a pattern which is normal, where that normal distribution has mean equal to whatever value is there, and standard deviation equal to whatever value follows. For example, suppose that IQ scores are distributed normally with mean 100 and standard deviation 10. We can use the shorthand notation to describe the distribution of IQ scores as follows. This notation says the same thing as this sentence. IQ scores follow a pattern which can be described by a normal distribution with mean 100 and standard deviation 10. So again, this notation is just shorthand, so we don't have to write those sentences over and over again. So for each of the following, use the normal notation to describe the behavior of the different variables. Pause the video and see if you can write each of these using that shorthand notation. The first one we have here is the weight of Red Delicious apples is distributed normally with mean 131 grams and standard deviation of 5. So notice that the variable that we're interested in is is weight in this case. We know that weight is distributed normally, so we use the tilde and the normal. Next, we'll fill in its mean and its standard deviation. It has a mean of 131 and standard deviation of 5. For the next example, we have the average number of acres used for growing tobacco in Kentucky is 75,300 acres per year, with a standard deviation of 5,000 acres. The distribution of the number of acres used to raise tobacco is normal. So, looking here, notice that what we're interested in is the average number of acres used for growing tobacco in Kentucky. So the thing we're describing is the average number of acres. So I don't just want to write acres here, I actually want to use my notation for the mean. Next, we're told that the distribution of the average number of acres used is normal, so we fill in our normal notation, and then we fill in our mean and our standard deviation. Recall on page 4, we looked at the density curve that looked like a box. In order to find the area under the curve, we looked at the rectangle that represented the area and calculated its height times its width. Or its width times its length, I should say. Similarly, we'll be interested in finding the area under normal curves. Finding the area under a normal curve is slightly more complex. There are 3 methods we're going to use to find the area under the normal curve. We're going to apply the empirical rule, which you saw previously. We're going to use an applet like the one at the length, or we're going to use what's called a standard normal curve. a standard normal table. And we're going to look in detail with lots of examples, all three of these. First, we're going to review the empirical rule. Recall that the empirical rule tells us if we go out a certain number of standard deviations away from the mean, how much of the area of the curve is contained within. So for example, if we go out one standard deviation away from the mean, then 68% of the data is included there. If we go out 2 standard deviations away from the mean, we have 95%. If we go out 3, we have 99.7%. For a review of these problems, visit the previous chapters for examples. Next, we're going to spend a lot of time looking at how to find the area under the curve using applets and using standard normal curves. For each of these portions, we're actually going to end this video there, but to kind of talk through the next 3 pages of the notes. So notice on page 8 is titled, How Can We Find the Area Under the Normal Curve with an Applet? At the top of the page, it explains that the empirical rule is limited because it only works if the values we're interested in are 0, 1, 2, or 3 standard deviations away from the mean. Located at the top of page 8 is a link to an applet. Go ahead and open up that link and get the applet up. And then there's an additional video listed in the notes where I'm going to work through each of the examples on page 8 using that applet, and I'll walk you through step by step. Once you watch that video for page 8, come back here to this video, and we'll finish talking about page 9 and looking at examples using the standard normal curve. All right, now that you have finished page 8 and you've looked at StatKey to look at different areas under the curve, now that what we're going to do is we're going to look at an alternative way to work each of those problems using what's known as a standard normal table. A standard normal distribution is a normal distribution with mean 0 and standard deviation 1. We use the letter Z to denote variables that follow a standard normal distribution. We can convert any normal variable to a standard normal variable using this formula. And notice this looks very similar to the z-score formula that you saw earlier in the text. We can also convert any standard normal variable to a normal variable using the following. When we convert any normal to a standard normal, the area under the curve is preserved. One of the most widely used methods for calculating the areas is the use of a normal table. A standard normal table is a table which provides area from under the standard normal curve. There are different versions of the table. A copy of the table we use has a table entry for the area under the standard normal curve to the left of different values of z. Use this method for your homework and StatKey to double check your answers, because on an exam you'll have to be able to use this table. So located in your notes is a link where you can find a copy of the standard normal table. There's also one provided for you on Blackboard. Also located in the middle of page 9 of your notes is a video explaining how to use the standard normal table. So follow that link, and that video was made during a previous semester, so ignore any class-specific content or page numbers, but that video is of me, and I'm going to pull up a standard normal table and show you how to read it. Once you understand how to read the standard normal table, and again, that video is going to go through that step by step for you, you're going to work problems showing how to solve problems involving normal distributions. To do that, we're going to follow these steps. You're going to write out the problem in terms of the original variable, draw a picture of the distribution, and shade the area of interest under the curve. Standardize the value or values of the original variable. Then, using that standard normal table, find the area to the left of the standardized value. Then you'll write your conclusion in context of the problem. So I'm going to show you lots and lots of examples that go through each of these steps. What we're going to do is we're going to rework all the problems we already solved using StatKey. You're going to use a standard normal table to do this instead. So if you'll notice, on page 9 through page 10 are lots of examples. The questions read the exact same as the ones we did for StatKey. So in your notes is another video where I'm going to work each of these by hand, and I'm going to refer back to that standard normal table so you can see exactly how to work each of these problems using that standard normal table. And we'll compare that to the values we got using StatKey. And what you should see is using either method, we're going to get the exact same answers. That video, when you pull it up, will conclude the Chapter 6 notes.